Okay, great. Shall I get
All
started?
right. So let me announce your last talk, the 4 lectures. So we are happy to have Dylan Butson giving his last lecture on vertex algebras from divisors and Calabi-Yau threefolds and perverse coherent extensions. And today is lecture 4. So please.
Thanks a lot, Jan, and thanks everyone who's managed to survive until this final lecture. That's really great. So today we're going to talk about more kind of fun stuff, connections with representation theory. And so the title is Representations of Vertex Algebras. Something in the chat. Oh, those are the slides, I guess. Great. Okay, so let's get started. So I'm quickly just going to remind you the main results that we discussed in the last few lectures, kind of on the more geometric side, which are we're going to use sort of in the applications today to study the representation theory of vertex algebras. So what did we say? We said that given toric Calabi-Yau threefold, together with some auxiliary object in the derived category, both satisfying some hypotheses, that there, first of all, there exists an unframed quiver with potential, Qy, Wy, it's depending on the choice of threefold here, such that there's an equivalence between the stack of compactly supported perverse coherent sheaves on Y, perverse coherent in the sense of Bridgeland, and we call this stack M of Y, and there's an equivalence between that and the stack of representations of this quiver with potential. And then similarly, using this object, M, we construct a kind of framed variant of this quiver. We sort of add a framing, such that we have a similar equivalence between the stack of representations of this framed quiver with potential and that of so-called F-framed perverse coherent extensions of the object M. So these are iterated.
Let me just double check. So M of Y depends on this object M as well. It's perverse coherent systems, or it depends on Calabi-Yau threefold only.
Sorry, M of Y does not depend on the object. Yeah, that's right. M of Y just depends on the threefold, or maybe you should think it's a resolution, so it depends on the map.
Okay, so I don't need to know what's a perverse coherent extension defining this M of Y.
That's right. That's right. Okay. But you do need to know what perverse coherent sheaves are in the sense of Bridgeland. And that just requires that you have a resolution, Y of some space X, satisfying some properties. But the actual map of the resolution is used in the definition of perverse coherent, the one that Bridgeland introduced.
So, sorry for interrupting you. Let me ask you a quick question. So, why, I mean, why do you need perverse coherent systems in this first line?
So it's not systems.
Any Calabi-Yau or any toric Calabi-Yau threefold gives rise to something. Yeah.
Yeah. So there's this theory of maybe people in physics call them brain tilings, or maybe in kind of combinatorial algebraic geometry, people call them dimer models, which I think allows you to associate similarly a quiver with potential to more general threefolds. Yes. But I don't actually know of a clear statement, possibly my own ignorance. I have never kind of waded through the dimer models literature, but I don't know a clear statement of actually the geometric stack that corresponds to representations of the given quiver. The issue is that, so the type of answer that we know under some additional hypotheses, where I would use the words perverse coherent, they allow us to identify a certain heart in DBCO, which corresponds to the plane modules over the path algebra of this quiver with potential. And in a more general setting, I don't know if the if a geometric description of that alternative heart is known. And
Yeah,
even
but it's I think isn't it a technical issue? I mean, because the definition, I mean, your construction, which you now recalling, it depends on homological whole algebras. And it's not really about quivers with potential. Even in our paper with Maxim, we didn't define it just for quiver with potential. It's more general, and it's as general as you can define it. I think, I don't remember, maybe Dominic tried to define it for any -1 shifted DG stack, or it wasn't him, maybe it was me. But anyway, people believe that Koha can be defined not necessarily for a chosen T structure in DB-Koch, but it can be defined in derived sense. I don't know. I see Adil Khan in the list. Maybe he can comment on that. But I mean, at least it's a general belief that you do not need, maybe not very general, but partially general belief that you can define Koha in DG setup, and actually not one half of it, but the whole thing. Yeah, but maybe indeed, maybe.
yeah, I sort of know, I think what you're alluding to, like there was this paper maybe of Bridgeland that explained that you can get kind of Drinfeld doubles if you construct sort of a derived
No,
category. But
it's not Bridgeland. I mean, Bridgeland, it's more general than Bridgeland. Yeah, I know this Bridgeland construction, which is pure formal. No, I mean that, how to say it? You mentioned that Koha, sorry, I mean, it's interactive talk, you know.
yeah, that's great.
Yeah, you mentioned last time, like the Koha gives you only positive part of some quantum algebras, which is
Yes.
true. And roughly speaking, the reason for that is that if you choose a T structure, like the values of the central charge belongs to the upper half plane. So then the question is, what about the lower? And when you work in the derived sense, you have also a lower half plane, and it's more difficult to make sense of Koha. That's true. But, and of course, the word theorem kind of kills what I'm trying to say, but hypothetically, there is a cohomological whole algebra for any. It's like in our, I think I wrote it in our paper with Mira and
Yeah. I know what you mean.
with any inconstructible locally arcing Calabi-Yau 3 category, you can associate Koha. Yeah, that's kind of
And
conjectural thing.
when you say Calabi-Yau 3, do you mean something that's like triangulated or abelian?
It's in the sense of our 2008 paper with Maxim. It's inconstructible, which kind of we defined it. It follows that the stack of object is a constructible constructible DG stack, but it should be also locally arcing. In, well, in the sense which I believe either explained there or somewhere else. So I mean, it's not geometric. It's sort of categorical, as you mentioned. Or did you, with any Calabi-Yau 3, in particular with a quiver with a potential, we can associate the potential as a function on the stack of objects of your it's a infinity triangulated category. Yeah.
Yeah. So right. So let me comment. I think that I agree with you in terms of more ambitiously. So certainly maybe you can define a Koha and you might hope to push some of the results like we've been talking about beyond the toric case, as maybe we discussed last time. And that might involve not necessarily being so wedded to these quiver type descriptions. And I'm kind of I'm sympathetic to that belief. But in terms of stating the theorem when you do have a quiver, the other point I was making is I actually don't completely understand or I'm not aware of a statement in the math literature associating quivers with potential to sort of more general toric threefolds that don't satisfy some of these hypotheses. So there's kind of two different things. One is about the generality within toric threefolds, and the other one may be just about going beyond even the geometric setting. Both are interesting, but for the purposes of the statement of the theorem, as far as I know, you really need these hypotheses, and I haven't been able to track down anyone who can tell me about Daimer models. But maybe I'll find some more.
Daimer models, it's a very simple thing. But just one remark before you continue. Again, in that paper with Maximum Koha, which kind of everybody cites, we defined it for equivalent smooth algebras with a potential. It's not just quiver, you know, and so it's more general. Slightly more general because equivalent smooth are homologically one-dimensional and potential makes it homologically three-dimensional, but it's bigger than just quivers. Okay, that's maybe, yeah, so when you have a generator, sufficiently good generator, then you can hope for its more general setup, which is mathematically well defined. Again, not at the level of a theorem about representation theory, but as for the Koha, I think it will be fine. All right, so sorry for interrupting.
No, that all sounds good to me. Okay,
Sorry.
so we have this statement. Oh,
Can I
was
also
there?
interrupt briefly
Sure,
related?
Yeah,
sure.
Yeah, it's just well, because I missed the last lecture, so I missed the connection between what you're explaining and the actual Koha stuff. So, but just from this discussion now, is it correct that what you're doing is like you start with this toric Calabi-Yau threefold, and then you associate this quiver with potential to that, and then you use that moduli space, and you look at like the Koha associated with that quiver with potential somehow. Is that what you're kind of going through this quiver story? Is that the idea?
Yeah, that's right. And I'll state very briefly on the bottom of this slide a bit more about what we said last time, so that could help. But yeah, that's right. What everything said sounded accurate.
Great.
So
right.
so we have this quiver with.
And then I guess what Jan is saying is that now there are ways, maybe partially or mostly conjectural, depending on how you look at it. But now that there are also ways to, kind of these ideas of Joyce and other people that you can actually start with, a general Calabi-Yau threefold with some orientation data and so on, and associate a Koha, like a three-dimensional Koha, to that directly without going through this quiver story, by using this kind of DG moduli stack of, compactly supported coherent sheaves on the Calabi-Yau threefold. And yeah, maybe so. I guess that's what he was saying. So
that sounds right. Let me just remark. So the nature of this theorem, in fact, is telling us that. Maybe I don't quite prove, or we don't quite prove exactly a strong enough form of the theorem to say this, but modulo a couple of details that maybe need to be checked, let me say the fact that we characterize the stack of representations of the quiver with potential that shows up, we give a careful kind of statement at the level of categories and also of moduli stacks of objects of this equivalence with the stack of compactly supported perverse coherent sheaves. The nature of that tells you that it is in fact true that the Koha defined, even in terms of this quiver with potential, if you like, is intrinsic to the threefold. It's not depending on any auxiliary data. And you could just as well, write down all of the correspondences and spaces that you use to define the Koha in terms of this model as the stack of compactly supported perverse coherent sheaves. But, and so it is clearly some just geometric thing. One issue is that I don't know the analogous part in more general situations that allows you to do this. And of course, this is a different part than just co. And so maybe you expect the coha to be different. My kind of intuition from working on this is that at least in the examples where we know what both are, that this perverse coherent part is kind of the right one for the representation theory purposes we're interested in. But there is, of course, maybe a possibility of considering the coha of actual coherent sheaves.
Right. Mm-hmm.
And again, maybe if you have some philosophy that you can build some bigger algebra, if you work with some kind of coha of the full derived category, then maybe that should be some invariant, and maybe you should think, oh, you'll get like different. I know there's a lot of stuff in the air, but I don't know actually any real results about this, but maybe there's some hope that you get like different positive halves from different T structures or something like that. And indeed, every time.
I recall that in that long ago, when we wrote that 2008 paper with Maxim, we had some kind of not very difficult theorem that if you have a three Calabi-Yau category with a nice set of generators, some spherical generators subject to additional condition on homes between them, then you can, of course, construct a quiver with a potential out of that. And there is a one-to-one correspondence between equivalence classes of categories with such nice collection of spherical generators and an equivalence class of quivers with a potential. In particular, if you change UT structure by a reflection at a spherical object, it corresponds to a mutation of a quiver with a potential. So in a sense, you get not quite, what you get is an invariant of the orbit, of the equivalence orbit. So I understand that you are saying that your construction is entirely canonical in the sense that this quiver kind of, it's carved in the stone when you choose these generators which you mentioned, like EI, I don't remember, or both of them. Yeah. So
yeah. And those guys themselves have a kind of canonical definition, at least in the setting that we assume, like the hypotheses of Bridgeland's work.
Yeah. Okay. Yeah. All right. So then you have a nice choice of generators. That's why you prefer Y to be kind of resolution, a small resolution of singularities.
Yeah, exactly. And I think that, like, my question always to people who tell me that you can do this for more general threefolds, and again, I'm not saying you can't, I'm just saying I kind of haven't, it's just an ignorance to me, but I don't know, just literally like, okay, so if you tell me there's some equivalence of the direct category of some threefolds, representations of a quiver, like what are the simple objects that correspond to the nodes, like which, and for like a more general toric threefold that doesn't have the smallest hypotheses I just don't know what the objects are, but I'd love to know. That would be great.
Yeah, okay.
Maybe I can just comment in the case that you have a vector bundle over something smooth projective editing exceptional collection, then there's something you can do also. Dominic had a student, I think who 5 or 10 years ago, who had a nice thesis kind of describing this sort of construction. Again, followed a different paper of Bridgeland. And so this allows you to do things like local P2 or P1 times P1. It's interesting, but certainly it's still not really, yeah, it's like a
local P2 is easy. Yeah, I mean, you construct of efficiently many spherical objects in your category. Yeah, that's okay.
But yeah, let's press on. Right, so we have this unframed quiver corresponding to the threefolds. We've now had some extended discussion. And then if we fix this auxiliary object together with this choice of additional data called a framing structure, which is essentially a particular choice of iterated extension of this object with itself, then we get this framed quiver with potential, and we get an equivalence between it and a certain stack that has a geometric description which we called the stack of F-framed perverse coherent extensions of M. And I'll recall an example of this on the next slide, just in the C3 case. But for now, let me press on. So the next main result was that following Jan's paper, we proved that there is a representation of the cohomological Hall algebra on the kind of categorified enumerative invariants that arise from this this stack of F-framed perverse coherent extensions. So again, I'll just recall here we by fiat defined the coha of the threefold to be that of this quiver with potential above, and this this vector space, the categorified enumerative invariant, as I called it, is the homology with coefficients in the sheaf of vanishing cycles determined by our potential of this, maybe pick some stability condition zeta, and of the stack of zeta stable representations of this quiver, the framed quiver. Okay. And moreover, we explained that this representation extends to a representation of a larger algebra, which roughly speaking is the size of an affine Yangian-type quantum group, which has a triangular decomposition in terms of the spherical subalgebra of the coha, which I denote SHOI here, and its opposite. Those are the kind of positive and negative parts. And so this representation, or its kind of adjoint, thought of as a representation of the opposite, you can kind of glue them together to build a representation of this bigger algebra. And that's where the kind of Yangian representations showed up in our story. And then the main application that we're interested in, that I'm focusing on today, is that we fix a divisor, a toric divisor inside of our toric threefold. Let's decompose it, the sort of underlying reduced subscheme in terms of irreducible components. And let's take the direct sum of the structure sheaves of the reduced irreducible components of the divisor, shifted down by 1. So sort of the semi-simplification of the structure sheaf of the reduced subscheme. So this is our object M that we have above. So it's going to give rise to some framed quiver. For every choice of framing structure, we'll get some different framed quivers. And in turn, we'll get some representations by the theorem above here of these cohas and these kind of Yangian-type quantum groups, which, as I remarked last time, look to be very similar to something that's quite actively being studied in physics under the name quiver Yangian by Lee, Yamazaki, other collaborators like Galikov. And so if we take this particular choice of object, we get these representations of these gadgets, then, and we pick a framing structure, we get this vector space underlying our representation. I denote it for simplicity just by VFS. And the main conjecture in this setting is that the representation of the Yangian-type quantum group determined by this divisor, according to what I just explained above, should factor through the algebra of modes of a particular vertex algebra, which I've denoted V of YS. And we defined these vertex algebras in the forthcoming preprint, draft available or upon request, as I've been mentioning, as the intersection of certain geometrically defined screening operators inside of a geometrically defined sort of free field algebra, which is some kind of big lattice type vertex algebra, which again, I'll explain more about in a minute. But the main thing I wanted to emphasize. Go ahead.
Go ahead, then I'll ask you a question, but do not turn the page.
Sure. I was going to say the main thing I wanted to emphasize today is that we had this choice here of framing structure, and there are different choices of framing structure, and these will give rise to different modules. So in fact, this technology allows us to construct various different modules over these vertex algebras and deduce kind of geometrically some relations between them. And that's what the talk today is supposed to be about.
Different modules over vertex algebras or different modules over this Yangian-type algebra?
So there'll also be different modules over the Yangian-type algebra.
Yeah,
that's also true, but I'm sort of emphasizing the vertex algebra perspective today.
So we return later to vertex algebra. This lattice vertex algebra, you know, since you are at Oxford, Dominique defined some lattice type vertex algebras which do not depend on the. Okay, so does this geometrically defined pi in your agrees with what he did. And actually, I even do not know how, because you have two Y and S, yeah.
Yeah, I don't think so. I have some speculations, which I would be happy to state, but maybe it would be better to state off the record, about the sort of potential relationship between Dominic's construction and the things we're describing here. But they are certainly not just the same. And maybe to say just in one word or one sentence, the main difference, our vertex algebras are defined such that their algebras of modes act on the homology of some moduli spaces of sheaves, generalizing the kind of Gronowski-Nakajima and AGT, like a la Schiffmann-Vasserot or Malikov-Kokov. Whereas Dominic's vertex algebras were constructed so that certain Lie algebras, which you can associate to them, are the Lie algebras which control the wall crossing phenomena for the given stack. So if you write the Conjecture-Soibelman wall crossing formula, there are some kind of products or maybe commutators that show up in the wall crossing formula. And he he claims to have sort of accidentally discovered even like the notion of vertex algebras, basically, from just studying these Lie brackets that show up in this kind of generalized wall crossing machinery that he has.
Yeah, you see, if I have, I'm confused. If you have Lie algebra or Lie superalgebra, so then you can hope to construct some vertex algebra, I don't know, by looking at the vacuum representation. Anyway, and for Koha, you know, there is this Lie superalgebra, but Lie graded Lie algebra constructed by Davison and Meinhardt. And you can try to construct VOA starting with that Lie algebra. So which one I get? Dominic's, yours, or neither?
The answer is something like maybe a special case of the ones considered here.
Yeah.
I mean, of course, you maybe also need to be using a special case of you need to be using a special case of end results as well. Completely assumed what we do here, but just to start quickly, the point of this BPS Lie algebra is the doubled Koha looks like the Yangian for, and the Yangian has a kind of quotient map to the envelope algebra of the underlying Lie algebra. And so if that Lie algebra like something like then its enveloping algebra would be sort of in the world of vertex algebras, and that might be a special case of the type of thing that we see here. So if you applied Ben's results to something like an ADE singularity times A1, which is the setting we'd be interested in too, to study things like affine algebras, there'd be some overlap, and you would see things like the affine algebra of the underlying ADE type showing up. And I'll talk a bit at the very end about affine algebras if we get there. By the way, let me just grab my phone to keep track of the time. I realized, oh, yikes.
Yeah, sorry for slowing you down.
No, that's okay.
You're not restricted to today as yesterday. You can go over time.
Cool. I'll try not to go too long, but yeah, we'll see how we do. We'll see how we do. Okay. So this is the main idea. We want to construct different modules over these vertex algebras, and I'll also introduce sort of the definition of these vertex algebras corresponding to these different so-called framing structures, which are like choices of iterated extension of our particular object. So let me give a concrete example. So there's this very nice paper which kind of inspired us to study this notion of framing structure in kind of more detail of Chuang, Kreutzig, Diaknescu, and Soibelman. And so the setting from our perspective that leads to what they did is the following. So you take Y to be C3, you take M to be the structure sheaf of C2, shifted down by 1. And you note that the self-extensions of this thing are kind of rank 1 over the X0 algebra. Of course, the X0 algebra is infinite dimensional, and that's something I kind of remarked on in one of the earlier lectures, that somehow taming this infinite dimensionality is part of the point of using the framing structures. But in any event, if you pick a framing structure, so that means you pick your favorite iterated extension of the structure sheaf of C2, then the resulting quiver that you get will be the following. So this is like a 3-dimensional generalization of the ADHM construction, except there's some auxiliary data, a sort of self loop at the framing vertex, which is, it's marked with a bullet here. And that means that you should not think of it as dynamical, in the sense that you do not need to specify an endomorphism of this framing vector space in order to define a quiver representation. So it's not part of the data defining a quiver representation, but it modifies, it's sort of a constant matrix that you fix once and for all, and it modifies your potential in the following way. And that allows you to build sort of slightly different quivers with potential, all from this same setup. So the choice of framing structure, like this iterated extension of the structure sheaf of C2, can be kind of captured in a choice of nilpotent matrix in GLR, where R is, you need to fix sort of how many copies of the structure sheaf of C2 you're going to take in this extension. So if we call that R, the rank of the, kind of determines the rank of the framing vertex in this quiver formalism, then you pick this nilpotent matrix and you add it in here in the sense that it modifies your potential, and you get some kind of different vector spaces. And just taking AF to be 0 corresponds to taking the underlying iterated extension of M to just be the trivial one, namely the direct sum of our copies. And if you make that choice, then this reduces back to the usual kind of, Ginzburg tripled variant of the ADHM quiver. And in that context, I'll just recall the sort of Schiffmann-Vasserot result with like this Yangian that you would associate to C3 should be just the Yangian of GL1 hat. It has a map to the principal affine W-algebra of GLR for NER, kind of a surjection, modulo issues about completion. And indeed, the geometric representation that you construct via the Hall algebra on the kind of the vector space that you build from this choice of divisor, in the case where you just use the trivial framing structure, that's what this superscript 0 here denotes. This map factors through this affine W algebra. And this is sort of the proof of AGT that was given by Schiffmann-Vasserot. But it's important to note that when you do this, the module, the geometric module you construct, under this representation of the W algebra, I mean, if you think of it as a representation of the W algebra, it's not the vacuum module, but it's this so-called free field realization that was introduced by Fagin-Frenkel. So this module is just isomorphic to the Bach module of the Heisenberg algebra for the Cartan of GLR. On the other hand, what these authors that are listed at the top here, what they proved is that if you do the exact same construction, they used a lot of the technology developed by Schiffmann-Vasserot, but you do the same construction, but instead you take AF to be a principal nilpotent, which corresponds to choosing your iterated extension of the structure sheaf of C2 to be the structure sheaf of like, the rth order infinitesimally thickened C2, like spec C join X, Y, Z mod Z to the R. And if you choose that framing structure instead, you find, again, a representation of the W algebra, but in fact, it will now be identified with the vacuum module of this principal affine W algebra. And what I want to point out, there's kind of a cool thing you can just see sort of right away, which is that the kind of evaluations, the non-zero evaluations of simple roots against this choice of nilpotent correspond to the non-trivial screenings appearing in the Fagin-Frenkel free field realization. So this vacuum module actually sits inside of this Heisenberg-Bach module, and it's cut out by certain screening operators. And I mean, if you picture like the standard representative of a principal nilpotent in GLR, each of those non-zero entries, which kind of correspond to the simple roots, each of them kind of also corresponds exactly to one of the screening operators that you use in cutting out the image of the vacuum module under this embedding, the Fagan-Frankel embedding into the Heisenberg algebra of the Cartan. There's some fireworks going off in the background. Sorry if you can hear it. It's approaching Guy Fawkes Day here. So remember, 5th of November. Okay, so this is the kind of basic idea, and I'll spell things out a bit more, but somehow to say it all in words, studying these convolution algebra actions on moduli spaces of sheaves, sort of supported on a divisor, give you different representations of the vertex algebra, and somehow what it looks like, and a lot of the statements are still sort of conjectural, is that the process of sort of studying, rather than these Hecke modifications of sheaves supported along a single copy of C2, but maybe of rank 2, if you study instead modifications of sheaves sort of supported on this infinitesimal thickening, that is somehow capturing this free fieldization. So there's kind of a nice interplay between the algebra side and the geometry side. You're really seeing something a bit more refined about the representation theory. And that's going to be the core of the kind of constructions that we explained today.
So here I have a quick question on the Schiffmann-Vasserot. So that is the find GL1 and mapping onto the universal enveloping algebra of the W-algebra for GLR, and that R can be varying.
That's right, any R.
Okay.
The correspondence you should have in mind is that the GL1 here, I'll explain a more general statement later, still somewhat conjectural, but the 1 here is corresponding to the fact that the nilpotent is principal, which means if you think about nilpotents as corresponding to partitions under their Jordan block decomposition, it's single step, single block. And if you want more blocks to study more interesting non-principal W-algebras, you'll need Yangians of GLK, where K is the number of blocks. And that will correspond to more interesting threefolds as well, and I'll say a bit more about that later.
Dylan, this your last note, last remark. So two opposite cases, AF0 and AF kind of principal nilpotent, yeah. But if I'm in between, what's the geometric meaning of this? AF is so I should consider this fat divisor as roughly like as a maybe not roughly, as a quotient of polynomials in 3 variables by the rth power of one of them. This is my fat divisor, and then I get a kind of linear an action of this third variable, yeah, on the quotient. What's this Jordan normal form of it? What does it mean geometrically?
Yeah, I think I understand. Yeah, so let me say, so for example, suppose you took something with 2 Jordan blocks of size K and L, respectively, then the corresponding iterative extension of the sheaf of C2 would be like direct sum of spec C adjoin XYZ mod Z to the L plus that, spec C adjoin XYZ mod Z to the K. And if K plus L, I mean, I might be off by a shift of 1 in the indexing, but if K plus L is R, that will also be a different iterated extension of R copies of the structure sheaf of C2. So you could just like take the structure sheaf of C2 and direct it a bunch of times, or you could extend it a few times and a few other times. There are a bunch of different
basically you have as many interesting, I don't know, interesting interesting framings as there are partitions of R. Something like that.
Right, exactly. And those also correspond to all of the different partial field realizations of the principal affine W algebra, the so-called parabolic index maps last time. These embeddings into smaller W algebras, where the most extreme case is where you split everything up into sort of the abelian version, Heisenberg algebras, and then it just becomes this Bacon-Frankl realization.
Okay.
Great. So let's move on. Right. So now I'm just going to give the definition of this vertex algebra, the kind of combinatorial operator definition. And it's going to be in terms of like fixed point data. So it may be, a little bit hard to, parse time exactly how you should think. Some concrete a little bit. The basic idea is the following. So we fix this divisor, or this threefold in this divisor. And now let me just introduce some notation. So we have the following index sets, which enumerate the set of irreducible components of S. So we saw this one appearing already earlier in decomposing S, or S reduced into its irreducible components. So that's DS. We have Fs, which is the set of T invariant points. So the T fixed points inside of Fs, or inside of this, this divisor S. Similarly, the set of torus invariant compact curve classes and non-compact curve classes are denoted by this is a frac C and a frac S, sub normal S, because S is the surface. So, well, whatever, these are just some index sets which enumerate some of the basic kind of, basically the GKM graph of this threefold. And so we have a decomposition, as I was saying before, of the underlying reduced subscheme into these irreducible components. And then the divisor will be able to be written as a sum, the underlying V divisor, as a sum of those corresponding to each of the irreducible components, but with some multiplicities that correspond to sort of like how thickened the actual non-reduced divisor is. And these determine some list of integers or positive integers, which play the role of kind of the rank in the construction. So in terms of the quiver, that will determine our rank for which we need to choose this framing structure. So for each of these irreducible reduced components, which is going to just be some smooth surface inside of our threefold, we'll define the kind of free field or lattice vertex algebra associated to it as the tensor product of the lattice vertex algebra on H2 equipped with the intersection pair with just a Heisenberg algebra on H0. So this will just be one-dimensional. And this is the basic reason that this is the right thing to do, and the reason why it matches our geometric constructions in this sort of simplest reduced rank 1 case, is because the moduli spaces of coherent sheaves that we study do not have fixed first Chern class. And that's a sort of key innovation of our approach over the sort of status quo in the generalized AGT literature. So we're really considering some kind of Hecke modifications of these sheaves that modify them along curve classes, not just points. And so they change the first Chern class of the underlying sheaves. And that's the reason you see a kind of bigger vertex algebra here compared to what Grinos Nakajima would assign this.
It's sort of important thing because you have new discrete parameters. It's not like second Chern class or something like that.
Exactly.
Yeah. So again, your V is what? It's
the lattice vertex algebra, and then down below is a lattice, namely the second homology, equipped with the intersection pairing.
And pi is another.
Little pi is, or big pi over here. Yeah, little pi is just a Heisenberg algebra.
Just a Heisenberg algebra. Okay.
So like this lattice vertex algebra has a Heisenberg subalgebra. And if you just took that instead, so this big vertex algebra has a subalgebra, which is a tensor product of the Heisenberg algebras on H2 and H0. Of course, there's no H4 and H odd because this is some one compact algebraic surface, toric algebraic surface here. And so this, if you just look at the subalgebra, which is the Heisenberg subalgebra, this agrees with what Gronowski-Nakajima would assign. The Heisenberg algebra on the, pardon me, the fireworks are very loud. The Heisenberg algebra on the homology of the surface. But
here the missing is H4, right?
No, no.
right, but it can't be
Zero-
compact.
Yeah.
So H4 is 0. Well, maybe if it's
This is
more
two-dimensional,
than-
complex two dimensionals.
Yeah, but it's non-compact.
Yeah.
Maybe I should say H0 is trivial and H4 is not, but let me not worry too much about that.
It's something where second Chern classes should live.
Yeah, well,
Because they normally live in a core, yeah. And this
yeah,
dual,
I'm not sure.
no?
Well, I don't mean no to your, just the statement. I'm not sure if you think of this as being where the second Chern class is. It's more just, the statement of Gronowski-Nakajima is that you find a Heisenberg algebra on the homology. And I mean, maybe there's convention choice here about H0 versus H4, which I don't want to dwell on. But the point is, this is some sort of extension, some larger vertex algebra, which as subalgebra contains the standard Gronowski-Nakajima. It was just showing up because it shows up in Gronowski-Nakajima.
Okay.
Now, really, we need to be in the kind of equivariant setting that I was explaining for this base field, the localized equivariant cohomology of the subtorus of the toric structure torus preserving the Calabi-Yau structure, which I'll call T. So really everything is over F equal to this H tilde bullet T of a point. And in that sense, this description that I gave here is a little bit of a lie, but you're still morally taking the same vertex algebra. It's just you kind of use the localization style description of the equivariant homology of your surface. And concretely, you can describe the vertex algebra of interest as generated by some Heisenberg generators, one for each of the fixed contained in your surface. So this follows just from usual localization arguments. And then in order to build this lattice extension, which comes from H2, you introduce for each toric compact curve class contained in your surface, you introduce an auxiliary generator, which is a kind of exponential vertex operator. The types of vertex operators that, I mean, you might not be familiar, I'll put the formula here, the types of vertex operators that show up in the construction of the lattice vertex algebra. So here the GYs, as I said, are some Heisenberg generators, which, they satisfy the following OPE in terms of here, the equivariant Euler classes of the tangent spaces. And then we have these extra generators, which are, again, there's some numerical coefficients in our base field determined by the geometry. These phi's are just the bosons corresponding to these Heisenberg algebras in, again, the usual sense that people mean when they define lattice vertex algebras. And here, for each curve class, we have this vertex operator where we take the bosons corresponding to the fixed points at sort of the 0 and infinity of the compact P1, which is labeled by this index I. And so these vertex...
Where is compact? I mean, I am confused. Is it the C? It's C compact curves. Okay. So.
That's right. Yeah, exactly. And I'll have a picture on the next slide where I kind of show what all the information kind of looks like, quote unquote, if you draw it on the moment polytope. So, they're a bit of a mess so far. Right, so this tells us how to define the kind of each of the factors of the free field vertex algebra that we're interested in. And then, oh no, there should have been more pauses there. So, well, we'll just with it. So on this first line here, we'll just define the total free field vertex algebra, this pi of ys, as the tensor product of reduced irreducible components of these lattice type vertex algebras pi of y SD that we just introduced above. And then we tensor them to the multiplicity with which each of the full divisor S. So the divisor S is kind of determining the rank of the GLR or of the kind of version 3 sheaves in the classical story. This is our free field vertex algebra. And now to define the full vertex algebra, we need to introduce some screening operators. And we do that as follows. We pick some presentation of the structure sheaf of our divisor as itself an iterated extension of the structure sheaves of the components, sort of as follows. This is my notation for a composition series. So OSD1 is the subobject, OSDN is a quotient object, the rest are some subquotients. And then for each of these pairs, sort of for each of the extension classes that's between these reducible components of our divisor, and each non-compact curve class, which is contained in the intersection of the two corresponding components, SDK and SDK plus 1, for each of those, we introduce a certain screening operator.
So is it sort of a combinatorial construction? Because as far as I can say, you look for the normal bundle of a curve, probably, which I don't know. Is it a common curve kind of for two intersecting components, or what is it?
Yeah, that's right, exactly.
Should
and then
I
you look at it sort of normal bundle.
polytope CW complex of which kind of contains all encodes all the intersections, all the divisors, and associate these things to combinatorial data, to faces.
Yeah, that's exactly the idea. Yeah. And then, of course, what I'm going to say is that we'll then define our vertex algebra as the intersection of all of these screening charges.
Okay.
So on the next slide, I just have a little picture of this. So this is a picture. Let me just say, before you look at all of the kind of decorations on this picture, in the background, there's some lines here. And so I claim that this is a picture of the resolution of an A singularity times the affine line. And the point is the following: if you have a toric Calabi threefolds and you look at its moment polytope inside of R3, so you look at the kind of real moment maps for the symplectic S1 actions inside of the C stars, that gives you some, vibration over a polytope inside of R3. And the Calabi-Yau condition ensures that you can faithfully project edges, and vertices of this polytope. So everything except the kind of bulk of the polytope, you can faithfully project them onto the blackboard.
Yeah,
and so we
is it? Yeah, but I'm kind of confused. If you have a Calabi-Yau torus, yeah, C star cube. Well, you can get rid of one factor, and if you inside look for a compact torus and just for the moment map, probably that's exactly what you have as an image of the moment map. They call toric diagram.
Yeah, that might be equivalent to the statement I said. Yeah, maybe that's correct. Yeah. I mean, I find it useful to have a 3D picture in mind as well. Like somehow all of the toric data is really pictured here. This is the whole moment polytope, but yeah. And so the way you should read these pictures is maybe the most important feature is that you can successfully read off the characters of the torus on the tangent spaces at the fixed points or the normal bundle to the fixed curves You can just read them off from the picture, and they're kind of the axes you should think are kind of labeled like epsilon1, epsilon2, and epsilon3 equal to minus epsilon1 minus epsilon2. That's the Calabi-Yau condition.
It depends, you know, physicists prefer to multiply them, and when they consider additive, it's something like h bar 1, h bar 2. I mean, there is a whole mess in the notation. Yeah, but yeah, I understand what you mean. Yeah.
And so now remember, for example, the most elementary generators of our vertex algebras were these like Heisenberg currents associated with fixed points inside of each of the components of the divisor. And so here you see, like, for example, there's this JY1, and there are going to be RD1, many of them. And if you want to read off the level of this Heisenberg algebra, it's going to be epsilon1 times epsilon2, because you get this sort of tangent space is successfully pictured here. Whereas, say, if you looked at this one, it would be like epsilon1 times epsilon3 would be the level of this copy of the Heisenberg algebra we're including. And so the overall idea of what happens in that kind of combinatorial construction I just explained is that we encoded the geometry of this threefold by building up this vertex algebra out of a bunch of different Heisenbergs and lattice vertex algebras, which are all at very specific levels relative to each other in a particular way that is encoding the kind of geometry of the threefold. And that's going to be the fact that all these levels are tuned in a very particular way, and the screening operators are kind of normalized relative to the levels in a very careful way. That's the thing going to give rise to the very interesting special vertex algebras that come up. So even though it looked like maybe it was a bit tautological and I didn't put a lot of interesting information into that construction, it turns out that you build very nice canonical presentations of interesting vertex algebras from this formalism. Okay, let me go on. So one particular class of examples that you can study, as I was alluding to earlier, is the resolutions of the following family of singularities, which are labeled by two positive integers m and n, sort of generalizing the usual an singularity times c family of examples. So let me call these ymn. And if you choose, excuse me, if you choose partitions mu and nu of length m and n, so not like the total number of boxes, but the number of columns, they determine a divisor S mu nu inside of this ymn. And the conjecture, which I stated last time, a picture of the way that the divisor is determined by mu and nu, the labeling of the moment polytope indicated. The conjecture is setting that the relevant kind of geometrically constructed Yangians will actually be the Yangians of GLM/n hat, the affines. And I learned of this conjecture from Kevin Costello in a lecture he gave at MSRI in 2018, I think it's recorded. I mean, personally, I learned the conjecture maybe earlier just from him, but in particular, it's documented there if you're interested. And this has been to some extent confirmed by the parallel calculations happening in the physics literature, but I can't really comment on how exactly what the state of the art is there. But moreover, the relevant vertex algebras in this setting are expected to be these general type A affine for any two nilpotents, f mu and f nu, determined by the choices of partitions. And here n are like the total size of the partition, sum of all the mu's. So m0 is also n, and n0 here is also n.
And what is this sigma in the notation?
Great question. So this is sigma here on the right-hand side is the shift. So there's a notion of shifted Yangian, and sigma was the notation that Brundon and Khloshchev used for a shift of real roots in the finite setting. And the conjecture here is, in fact, that you should get the shifted Yangian of affine GLM/n, where the shift matrix is determined by the intersection numbers of your divisor with the compact curve classes. So here I've denoted the 4 compact curve classes, C1, C2, C3, and C4, in this resolution. And then on the right-hand side, I've correspondingly drawn a choice of symbol roots inside of the GL3/2. This is the 3-2 example. And so you look at the intersection number of your divisor with each of these curve classes, and that determines the shift corresponding real root in this affine Yangian. These are exactly the shifts that would be consistent with having W-algebras as quotients in the finite setting, according to the Brendan-Kleist results. And you see that it sort of very beautifully naturally appears here from the geometry, the intersection number of the divisor with the compact curve classes. And maybe I should say, like, these conjectures in maybe a slightly less precise form, I think are due to Rapcak. And the perspective that we have here is combining maybe some insights that I learned from Kevin Costello with some of the predictions in the Rapcak papers.
I remember that, I mean, Rapcak, it's rather algebraic story, but in this geometric terms, I think it's in our other paper with in the same group, Mira, Yapin,
right,
Gufang, where we discussed the shifts in Yangians in relations to different chamber structure. Yeah, I think it's.
I should have mentioned that. Yeah, so some, I mean, I think that Kevin's conjectures slightly date your guys' paper.
Yes, of course.
But
yeah,
I know that you guys checked this in some examples. Maybe I should also mention, I think Henry Liu's thesis checked this for, seeing the -1 shift for the action on the cohomological BTCs of the threefolds, which I think you guys also maybe checked something like that. Somehow there were some of the statements in your paper that I think more threefolds differed slightly from the version of conjecture that I stated here. I mean, it might still be technically correct, but I think maybe we're quite philosophically correct.
As for that, I need to recall exactly what was written in that paper.
Yeah, we could maybe talk about it later off the record. But no, certainly it's true that I think the most forceful computations to explain the occurrence of shift and its relationship with geometry are in that paper. That I think there's some nice computations there, which, yeah, I did follow a lot of the ideas from that in writing these things, but then there were also some things that I think were not quite understood correctly there. So yeah, we can talk about it off record. Yeah. Okay, great. So the basic story that I mentioned at the end last time, that you should be able to recover some kind of affine version of the Brendan-Kleist isomorphisms from this kind of geometric setup. And there's some results in this direction in pure algebra, but I think that this geometric approach has a lot of promise to kind of resolve this.
The author of Brendan has a very difficult name to pronounce. It's Klishov.
Klishov.
Yeah, it's like Goethe. I mean, there are many difficult.
Yeah, you'll have to excuse my kind of American accent.
This sound, it does not exist in too many languages. Yeah, okay.
Thanks, though. I do like to know these things as kind of cultural fun. Okay. So this is the sort of story that we'd like to prove. And now let me tell you a bit about the main way that we approach proving, for example, something like the right side. So in the forthcoming preprint, there will be at least an outline of the proof of this in the case that capital N is 0 or little n is 0. So the kind of not necessarily principal affine W-algebras we successfully identify in this geometric framework. So how do you do something like that? The main point, which I mentioned last time and is related to coproducts on Yangians, but I won't dwell on that today. The main point is that if you're able to split up the structure sheaf of your divisor itself as an extension, then we prove that there's an embedding of vertex algebras from the vertex algebra you'd associate with the big divisor into the tensor product of the vertex algebras you'd associate with the kind of each of the components, where the image of this embedding is described by the kernel of a single screening operator corresponding to the kind of extension class that got forgotten, split OS up into OR and OT. So there's some extension class between these two guys, OR and OT. And that corresponded to kind of one of the screening operators in the definition of V of YS. And if you forget that, then you get this vertex algebra embedding. It's not an especially hard thing to prove, so I didn't call it a theorem or anything, but it's a very nice, sort of philosophically nice result. And you can kind of pick in this geometric kind of way of picturing things I've been explaining by kind of decomposing, like if you have some labels on your spaces of the moment polytope, which determine your divisor, then you can kind of split them up as a sum, and you should expect a kind of embedding of the vertex algebra associated with this divisor into the tensor product of the vertex algebras associated with these divisors. That's the kind of calculus for these vertex algebra embeddings. And as I was
respond, hold on. Do they correspond to something to this factorization structure on Koha?
Yeah, it does definitely seem like that. That's right. But that's still kind of in progress. They also, there's this kind of funny paper which followed you guys' ideas. This paper of Chris Elliott and Filtration-Yu, where they conjectured a certain kind of factorization structure in the geometric Langlands correspondence as the ranks of the groups varied. So if you consider geometric for like GL or SLR, and you consider different R's and the way that they all fit together, they had this kind of sheaf of categories factorization conjecture. And this seems like they also have some conjectural relations with things like related to parabolic induction, like geometric Eisenstein.
Yeah, exactly.
And these maps are giving like these parabolic induction maps for W-algebras, as I was just about to mention. So it does seem like it's all very closely related. And of course, I mean, there's this, I'm basically just talking to Jan now, sorry, but this kind of categorical, conjecturally equivalent construction that I explained in terms of the Langlands categories. And this also seems to kind of fit into this philosophy. Let me
great.
That now.
Because this factorization structure, we noticed it Maxim and toy model just in that 2010 paper at the level of Koha, that we define the notion of factorization sheaf. And I don't know, probably that, so then probably it's, but it's kind of a toy model of what's going on. We did not consider vertex algebras, of course. We just work with equivariant homology of different moduli stack without additional structure. But right, so
yeah, I'm familiar. Yeah. But somehow I think that was influential to Phil saying in Chris's paper, and then them in turn to mine. So I think it is all kind of the same.
But this is much nicer. Okay, yeah.
Okay, so we have these parabolic induction type maps, and so I was just about to say, so in the case Y is C3, and we take our divisor just to be R times C2, then these parabolic induction maps, or these kind of factorization maps, as I called them, between the vertex algebras, the setting, as I was describing before, is what corresponds to the Schiffmann-Vasserot and Chuang-Kreutzig-Canescu-Soibelman results. And these kind of give a geometric interpretation of this co-product on the affine Yangian of GL1 and its relation with the parabolic induction maps between affine W-algebras, principal affine W-algebras, which appear here. And then the expectation, is this what I have written next? Right. The expectation is that the analogous, so there are parabolic induction maps for more general, not necessarily principal W-algebras. They were studied, for example, by Naoki Genra, and using kind of so-called generalized Wakimoto resolutions. So these are certain resolutions of general, not necessarily principal affine W-algebras, which kind of interpolate between the Wakimoto resolution of the affine algebra and the Fagan-Frankel realization, pardon me, I said resolution, realization of the affine algebra, and the Fagan-Frankel realization of the principal affine W algebra. So the expectation, I'll explain the kind of simplest example of this in a second, but the expectation is that this realization structure in the kind of more general case is going to recover a whole bunch of nice information about the representation theory of W algebras, of which has been recently constructed, but some of which is sort of still open, and this actually gives a new approach to proving some different results in the representation theory of affine W algebras. And one of the things that this makes most transparent that's really cool, which I have time to say too much about, and probably you wouldn't get much from it anyway if you'd never heard of this, but there's this notion of inverse quantum Hamiltonian induction, which has been of a lot of interest in the Vertex algebra community lately. And the statement is that you get embeddings of less principal affine W algebras into more principal affine W algebras. So for example, if you looked at like, you know, the affine algebra, it should have an embedding in principal affine W algebra tensored with some free fields. So sort of a relative free field realization. And you can see all of this structure very clearly from this kind of geometric construction that we have. It's very cool. And if you're interested in learning about parabolic induction and inverse reduction, let me just say there's a paper of Adamovich, Kreutzig, and Genra, which describes all of the sort of structures in the GL3 case, which is kind of the simplest non-trivial example.
Dylan, if kind of someone is not interested in particular classes of W-algebras or even vertex algebras, is it possible to spell this story as representation theory just entirely in the language of factorization algebras, kind of very, very generally?
You mean the distinction between like factorization or chiral algebras, like in the sense of valence and Drinfeld and vertex algebras?
Yes, exactly.
Yeah. I think it is definitely possible, but I'm not sure if it would be additionally enlightening to use the chiral. Like I've used the language of vertex algebras throughout these lectures, but I'm very partial to the valence and Drinfeld language actually for describing these kinds of things. I'm not really a vertex algebra person. I've read much more of valence and Drinfeld than Frankel than Zvi. Or should I say Ben Zvi Frankel? But in any event, I'm not sure if in this particular setting using that chiral language would especially be easier. Maybe the only place I would say it most obviously would be better is in this kind of factorization to categorical formalism that I was alluding to before. But again, basically just talking to Jan here, so maybe let me not dwell further on that.
Okay, go ahead.
Okay, great. So now I think, I don't remember exactly what's on the last slide. Right. So this is the last slide, more or less. And it's kind of, again, I can't use this pause feature to slowly reveal it to you because there's a diagram, but let me just put it all out here. So this is the setup, which should give rise to the affine algebra of GL2. And I just want to explain what all this kind of structure looks like in the simplest example. So here we're considering a resolution of the A1 singularity times C, why we expect to see sort of SL2 W algebras showing up. And there should be a divisor determined by any partition of length 2. So in this case, we're going to take the partition 1, 1. And of course, in terms of a nilpotent inside of GL2, the partition 1, 1 just determines the 0 potent. And as a result, the W algebra we're interested in, if you try to take the W algebra for the zero nilpotent, it just gives you back the affine algebra. So this is kind of the least principal, the kind of trivial affine W algebra for GL2. And the corresponding divisor looks like you label the faces of the moment polytope by 2, 1, and 0, 0. And now the claim is that if you kind of consider the geometric setup that we explained before, so you introduce these Heisenberg generators corresponding to the fixed points inside of the reduced irreducible components, and you introduce these lattice generators for the, in this case, the one compact curve class contained in one of these reduced irreducible components of the divisor. And then you introduce screening operators for each of the non-compact curve classes that feature. So we have 2 screening operators, Q1 and Q2. Then the intersection of the kernels of these screening operators defined geometrically should be precisely this affine algebra. So how do you see this? So let me work backwards. So first, if you consider the kind of completely factorized free field algebra, it's just given by a tensor product of 2 Heisenberg algebras and a single kind of what people like to call a half lattice vertex algebra, which you can, if you like, think about as chiral differential operators on C star. And now, if you look just at the kernel of Q2, which embeds into this, so that's some vertex algebra that's denoted here, it will look like a tensor product. So Q2 doesn't touch J1, so the tensor factor of the Heisenberg algebra just associated with J1, nothing is going to happen to it here. But if you look just at that, if you look at the other factor where Q2 does interact, it kind of screens some subalgebra of the algebra generated by these 2 Heisenberg currents J2 and J3, which are kind of adjacent to the edge at which the screening operator kind of is acting. You find that inside of here, you find chiral differential operators on A1. And the kind of embedding of this factor into this factor is what people call FMS bosonization in the kind of classical vertex algebra literature, but it's just the restriction map from chiral differential operators on A1 to chiral differential operators on GM, or C star inside of C. And now, having identified this with the tensor product of, well, it's 2 Heisenberg algebras and chiral differential operators on A1, the remaining screening current, the Q1, which we had to forget to get the embedding into this vertex algebra, can be identified with precisely the Wakimoto screening operator. And so, I mean, if you've never heard of Wakimoto modules, this might not be helpful, but there's some kind of canonical embedding of the affine algebra into CDOs on the big cell tensor with, an auxiliary Heisenberg algebra. And the geometric screening operator we find here is precisely the Wakimoto screening under some appropriate identifications. And then alternatively, if you first forget the screening operator Q2 and embed into just the kernel of Q1, tensored with this other guy, then you naturally get this factorization because Q1 doesn't talk to any of the generators of this kind of lattice subalgebra here. So you still have this pi 0, this copy of chiral differential operators on C star. But then in this factor, you just have 2 Heisenberg currents screened by a screening operator Q1 corresponding to this curve class. And this is precisely the same local picture we had just in the C2 case. And we know that this screens, this is just the Fagan-Frenkel realization, and it screens the principal affine W algebra inside of these 2 copies here of the Heisenberg algebra in the sort of full free field realization. So we find a tensor product of the affine W algebra of GL2 with this, this so-called half lattice or copy of chiral differential operators on C star. And the embedding of the affine algebra into these, which is kind of induced by forgetting this Q2, i.e. if you like look at the screening operator Q2, it's precisely the one that shows up in the work of Adamovich, which discovered the original example. This is it, the original example of so-called inverse reduction. You're getting an embedding, a sort of relative free field realization of the affine algebra into the principal affine W algebra, the kind of more principal W algebra. In this case, there's only one to go to. There are only two orbits in the nil cone. And the screening operator Q2 can precisely be identified with the screening operator that Adamovich wrote down, which screens this embedding. So we find this very nice compatible picture of the Wakimoto realization and the Adamovich realization of the affine algebra of SL2 from this geometric picture. And it turns out that you can more or less identify the same story happening for all of the type A principal W algebras. There isn't as much technology available in this super case as of yet, which, I mean, to my eye, that's kind of a good thing in the sense that it means geometric construction maybe is good for something. It's producing new representation theory results. As a result, it's still conjectural identification in the supergroup case, but the usual case is fine. And then finally, maybe I should stop for questions, but probably this is all too confusing to ask questions anyway. But let me just remind you, in the very beginning, I was telling you that the different choices of framing structures, which concretely translated into different choices of framings on certain quivers, framed quivers with potential, that these should correspond to all of the different kind of modules that can show up between the vacuum module and the free field realization. And so if I can just zoom out, you can still see what I have here, right? So here is a draft of our paper. And here are the pictures of the corresponding quivers that show up for each of the four cases. And so you can see that as you sort of throw away more of the framing structure, you increasingly trivial framing structures, you get sort of simpler quivers for which you expect the critical homology groups of these quivers with potential, can't see the potentials for the last ones, to be precisely those modules, those four different modules that were occurring on the previous page. So here we have the vacuum module of the affine algebra, we have its Wakimoto module, we have its inverse reduction realization, and then we have the full free field realization here, just a tensor product of two Heisenbergs and a half lattice. And the partially conjectural kind of result is that this corresponds to some natural maps that you get in this geometric setting from varying the choice of framing structure on this quiver. All right, I better stop there. Thanks everyone for listening. It was great giving this lecture series, and of course I'll be happy to answer any questions, at least for a few minutes here.
Thank you very much. Yeah, for the last part was for people who like vertex algebras really by heart, and so for them probably this dictionary between different type of extensions, geometric kind of choice of framing, and different vertex algebra, different representations. It's indeed something which they didn't know, had no idea. So I have maybe a kind of more general questions. So one is related to that. You mentioned Beelenson and Drinfeld, yeah. So the Lie algebras, like, I don't know, affine Lie algebras, generalization, it's sort of a local objects. They involve sort of a formal disk, a formal neighborhood of a point on the curve. Now, if I'm interested indeed in the global story, like, I don't know, chiral algebras, which you mentioned, either a global version, how to add the curve to this construction.
Yeah, maybe I could say something. So I think if you want to if you want to make a statement about a correspondence between geometry and kind of representation theory, but which uses the global curve on the vertex algebra representation theory side, then the types of statements that I think are most natural are those that appear in really the original AGT conjecture. This thing that was proved by Schiffmann-Vasserot, Malikov-Kunkov, it's some variant of one of the things conjectured by AGT, but their original statement was about conformal blocks of these vertex algebras, which is, of course, the natural global invariant that you have if you try to put this vertex algebra on a curve. And the statement is that if you pick a curve, and maybe you need to pick also some sort of deformation of it to a point in the zero-dimensional strata of the Deligne-Mumford compactification, like you need to sort of decompose your curve into a chain of rational curves with only, 3 marked points, then that determines a class S gauge theory by this famous work of Gaiotto, the n equals 2 dualities paper. So a choice of curve and an ADE type determines a 4D n equals 2 gauge theory. And these are precisely the types of gauge theories that people like Donaldson studied to define invariance of 4 manifolds, also famously in work of what mathematicians call Seiberg-Witten theory, following sort of indirectly the work of Seiberg and Witten. So the statement is that the partition functions of these 4D n equals 2 gauge theories, which are determined by the choice of curve and ADE type. So these are some kind of decorated Donaldson invariants. They should be conformal blocks of the relevant vertex algebra on the curve that you use to determine your gauge theory. So it's sort of telling you that if you study these different decorated Donaldson invariants for different curves, and then you ask, like, what are the sort of gluing rules as you kind of glue together your curve out of, chains of P1s, those gluing rules for these decorated Donaldson invariants obey the rules that a conformal block needs to obey for these vertex algebras. So these vertex algebras are kind of like the universal invariance of the kind of 4 manifold, or in this case, it's a divisor and a threefold, whatever, the kind of universal invariant, which knows about all of the different decorated Donaldson invariants for all of the different choices of curve. And the way that those glue together are kind of determined by the way that the conformal blocks glue together for this vertex algebra.
But how to see the Calabi-Yau geometry from this perspective?
I mean, in this case, I guess the divisor is sort of playing the role of what I was calling the 4 manifold. So instead of Donaldson invariants, maybe you should be studying, I don't know what.
Yeah, but
maybe algebraic geometers would still call them Donaldson invariants, kind of invariants of surfaces.
Yeah, but that's the problem, because Donaldson theory, even if you think in these terms as a D4 brane, so it has to be smooth. And now you have a singular, you have like 3 coordinate planes, or even 2 coordinate planes in C3. So I don't know, either any kind of, I remember I spoke to Emmanuel Diaconescu. He told me that physicists did not quite understand that story.
Yeah, I'm not quite sure what to say about that either. I'm sympathetic to the complaint.
No, it's rather, I'm just curious, it's a Q&A session. I can ask any question and you can give me any answer. For example, I can ask you a question that in your story, you saw coha of a Calabi-Yau threefold acting on some cohomology of the frame moduli space, but you know, Koha is just sort of, it's kind of a Hecke algebra. Basically, we are talking about Calabi-Yau threefold, and we can construct different Hecke-type algebras using this correspondence. We can include divisors, but we can also include curves. Yeah, and there is this, you know, you certainly know this work of Olivier with Francesca and with Porta, maybe. I don't remember. Maybe with Diaconescu. Anyway, when they consider Koha, maybe with Eric. Anyway, you know this Schiffmann with different collaborators about Koha. I think they consider surfaces only, but they can maybe, but they also included curves, like Hecke operators corresponding to curves. So certainly you can upgrade it to Calabi-Yau threefold. And so what do you expect to get from this bigger picture? Because your curves, they appear apparently different in a different way.
I think it's similar to that. If I understand correctly, you're referring to something that has yet to appear, like their work in progress, or something that's on archive.
I did not. I have no idea.
I don't know. I think that if I understand correctly, I think the thing you're referring to is not yet out, but I am aware of it. And actually, I'm visiting Francesco in the week after next. So I'll learn more about it then.
Yeah, all right. It's interesting. I thought that it's kind of, it's already, let me check in the archive.
Could be wrong. Yeah,
No,
have a look.
That's right. Okay.
You won't be able to see if I check my email, right? So Francesco did tell me about this by email. And
oh, I don't see it. Yeah, you're right.
Yeah,
did not appear. Yeah.
So I think he said, yeah, together with Diaconescu, Porta, Schiffmann-Vasserot, I'm studying. Yeah,
okay.
there's no mention of an archive number.
All right. So yeah, good. Okay.
But I expect it's sort of similar, but there are some differences. For example, I think they're studying the Koha of honest, coherent sheaves on the surface, as opposed to I'm using this kind of Bridgeland trick of using the perverse coherence in his sense, which it does see kind of similar things. I expect the stories are closely related. And so maybe when I was saying that that was a unique feature of our work, I was excluding their yet to appear work. But indeed, they're also working on something similar, and I am aware. Maybe I should have mentioned it. Yeah.
And maybe a last question, because otherwise we will never finish. Yeah, you used sort of a Koha, which means that you use homology of stacks, but instead you can use constructible sheaves, and which leads to kind of a motivic whole algebra, and like maybe perverse sheaves on these moduli stacks, which I believe people also used, like Nakajima some time ago. Yeah, either a version of representation theory, if I replace coherent by constructible.
Replace coherent by constructible on the threefold.
Yeah, because you know, like the kind of the original approach via whole algebras to quantum groups. Yeah, it was sort of, it used constructible sheaves on the stack of objects.
Well, let me just make the distinction. We have these moduli spaces of coherent sheaves, but then we can, on those moduli spaces, on those stacks, consider constructible sheaves.
Yes.
You know, these sheaves of vanishing cycles are kind of that.
Yeah, instead of taking a homology, which you can take.
That distinction, right. then the answer is yes, right? There should be a, for whatever, maybe different choices of cohomology theory, there should be some kind of refinements. And it really is a concrete thing, like, yeah, basically my expectation is the same as what you know in the DT theory story. There should be a refined version, it should have more information. If you want to write the kind of 2-parameter generating functions of the flavor that I wrote in the beginning when I, maybe the last lecture when I wrote the Gush formula, really it sort of turns out, as I'm sure you know, that the cohomological degree is not kind of exactly the right degree. You should really be studying some more sophisticated filtrations, which maybe are easier to see in these more refined contexts. And, in order to link up with work of various other people, like, a lot of Ben's work, I think, really requires being in the, some kind of better category, like, keeping track of Hodge structures, that kind of thing, right? There's this, what does he say? Mixed, monodromic, whatever. There's some long list of adjectives.
I mean, this mixed, I think pure monodromic, it's what we also considered with Maxim, but it's rather a question about motivic origin of all that stuff. Because if you kind of even trying to work with motives, so these corollaries, including the Hodge theoretical aspects, they come more or less for free if you have done some considerable foundational work. That's actually I think in that paper with Maxim on Koha, we conjectured, or I don't know, it's not written as a conjecture, that you can work with Voevodsky category of motives and everything will work nicely. So, and indeed, kind of
the 2-dimensional or 3-dimensional one?
3D. Well, I don't remember, because in 3D we should okay, like, first let's forget about the potential, yeah. Then it's no more than 2-dimensional, it's 1 or 2. But then kind of conjecturally you can imagine that there is a homotopy version of the sheaf of vanishing cycles. Probably you can say more about it.
Yeah, I mean, for the 2D one, first of all, I mean, you can I mean, I proved that this Koha can be made motivic in the sense that the Koha structure exists already on the Voevodsky motive of the moduli stuff. I mean, I didn't write this explicitly, but it's kind of.
Yeah, I mean, instead of indeed this, when you add the potential, basically you work with kind of naively, you work with a category of exponential motives, which of course should be a realization of some exponential version of, I don't know, Voevodsky category or whatever category of motives people can construct. I'm not an expert, but at least the trend is that whatever enumerative result you obtain working just with K0 of the category of Artin stacks, or with hooked up cohomology, in the end, it is upgraded to an appropriate category of motives. Yeah. So then,
so I mean, if you're in the quiver with potential case, then you have I mean, Ayub has constructed a motivic version of nearby and vanishing cycle sheaves, which live in Voevodsky's category. So you can, one can use this to define this 3D profile for quivers of potential.
For 3D, again, ideal, probably it's exponential version. Instead of kind of a variety or a stack, you consider a stack with a function on it, something like that.
Right. I mean, yeah. I mean, there is some formalism of exponential, but I'm not sure. Yeah, I'm not. I mean, this seems more related to. I mean, because this thing is more about vanishing cohomology, right? Whereas the exponential motives is somehow about this kind of rapid decay stuff, which I'm less familiar with. But I think as far as vanishing
yeah,
cohomology is concerned, we just
yeah,
use
yeah, yeah. You should have, yeah, you should have some critical version. But anyway, so it's kind of, and the enumerative level, whatever you construct with cohomological whole algebra in the end turns out to be equivalent to whatever you construct with constructible with motivic whole algebra when you work with K0 of some category of motivic sheaves. So then probably kind of one can speculate, since Dylan is trying to generalize enormously that story. So then probably there should be a version at the level of, I don't know, some category of motives, which I cannot even describe.
Yeah, maybe this story can be made motivic. Yeah, but so somehow, like, I guess I mean, so what you're doing is, yeah, you're looking at this perverse thing. I mean, so I guess the whole, yeah, the derived version or Joyce version or so on. I mean, all these people, what they're doing is looking at this whole derived stack or DT stack of, yeah, coherent sheaves or, yeah, and you're sort of saying, okay, we don't want to look at, these kind of DT categories or moduli of objects in a general derived to a DT category. We just want to put some T structure and look at the hard, and then we just have an ordinary abelian category, and we're sort of working with this. But I guess that this should be some kind of, I mean, shouldn't this be some kind of subalgebra of the whole one? I mean, of the big version, maybe some important subalgebra. I mean, the one that sees a lot of the important stuff, I guess.
Yeah.
Yeah, I would hope so. I've been a little bit confused too about how I should think about the relationship between what people call moduli of objects in these sort of big DG categories versus the kind of concrete moduli of objects in abelian categories that we're using here. I would really like, though, to have a more careful understanding of the relationship. I think that a lot of the recent work of, people like Brav, Diekerhoff, Rosenblum, like some of that relative Calabi-Yau structure stuff that they've done, it seems like it could be really useful to formalize some of the phenomena we're observing here.
Oh yeah, actually, yeah, that's a good point. I'm glad that you recall, because there is, with Maxim we have some, it's still unpublished notion of Calabi-Yau category with corners, which contain this Brav-Diekerhoff, and it's kind of really useful when you speak about these boundary conditions categories. Yeah, well, that's a good point. Yeah, maybe, yeah.
And similarly with Dominic's work, right? Like I was mentioning, I have some speculations about how this might be related to Dominic's work, but again, he's looking at the homology of these stacks of objects in the derived categories. And yeah, I wish I was more clear-headed on the relationship, but I don't want to say anything on the record.
Okay, I will not tell him, so we we can turn off the recording, and so then you can say. All right, so more questions. Probably the thing which kind of I wanted to discuss about this Kimura Pestun, we will discuss privately by email because people are too tired.
Yeah, I should get going soon too. I'm supposed to go, it's 8:15 here. So
all right, so does anyone have a short question? Well, if not, let's thank Dylan for a really inspiring and wonderful lecture course. Thank you very much. Thank
you for inviting me. It was great. Yeah.
Yeah, all right. And so then this is it for today. Thanks again.